Okay, we will see the analog to digital encoding. Okay, so what we are using the pulse amplitude modulation in the PCM. Okay, we have seen the differential Manchester coding in the previous one. Now what we have to use the analog to digital encoding, means this analog signal we have to convert into the digital form without losing the data. Example means what, how we can lose the data if there is only video and no voiceover. So that is the losing of data. Okay, so for this we are using this pulse amplitude modulation, which samples the analog messages and generate pulses based on that sampling. Okay, so this is pulse amplitude modulation. So analog to digital encoding, the method is pulse code modulation. In this, we are using the analog signals. We are what then sampling that signal. We are quantization. We are what measuring the discrete values among that signal and then performing the binary encoding. For that, PCM, pulse code modulation, what it uses this Nyquist theorem to determine the sampling rate. Okay, so what will be the sampling rate? It is the twice the highest frequency of the original signal to ensure the accurate reproduction of an original signal using PAM, that is the pulse amplitude modulation. So the Nyquist theorem sets what determines the sampling rate, which is the 2x, and x represents the highest frequency. Now we will see the block diagram. Okay, wait a minute. So this is the analog to digital encoding. The first step is in what? PAM, means what? Pulse amplitude modulation, PAM. What is done in the PCM? The first step is what? PAM. This is our analog signal. This is the first step. In this PAM, the analog signal is sampled at fixed interval, and the amplitude at each sample describes the amplitude of the pulses. See, the frequency, the amplitude is of the pulse and is nearly same. Okay, so sampling is done, and according to it, the pulse on that particular intervals are set. Okay, now this signal is actually, it is not the continuous signal 0 1 0. It is not in the specified format. It is still the analog signal, because the pulse can have any amplitude. Okay, see, the amplitudes are not same. We have seen in the starting of this lecture, the digital signals are having the same amplitudes, means in only 0 or 1. Multi amplitude system is available in only analog signals. So this is also one of the form of the analog signal. Now next, what will be the question? How many samples we have to take? Okay, we are taking the minimum samples, or if we omit one of the sample, then there may be loss of the data. So the maximum samples we should take for avoiding the loss of data. Next step is what? Quantization. What is that? We are doing the measuring. Quantization means what? Actually, we are performing rounding. Means what? Here we are giving the minus 127 to plus 127 interval. Means what? We are rounding the sample value to nearest quantization level. Means plus 127 minus 127. We are what? Rounding with one of the nearest value. Okay. So there is what? There is no fixed value, means infinite values are there. So here we are actually setting the boundaries for that signal. That is the quantization process. Means what? We are approximating the real world value with the digital representation, which what? Limits the signal, or we are what? Providing the range of the values for that particular signal. That is the second step. The next step is what? Binary encoding. So what happens in binary encoding? We are transmitting the data into the 0 1 format. So that is the binary encoding. On this data, then we are applying the digital encoding technique for what? Transformation purpose. Okay, wait. Present. And then we will what? Transfer the data, direction of the transfer. We have set the limits from this to this, and we are setting the direction, that is the analog to digital encoding transmission. Are you getting this? Remember this diagram, and we have to draw the whole diagram, and we have to write the steps for each: this spam, this quantization, binary encoding, digital to digital encoding, direction of what? Transfer. And this PCM, pulse code modulation, is commonly used where it is used to transmit voice signals over a telephone line. It gives a very good voice quality. Okay, so next we will see the next method, digital to analog encoding, used in transmitting data from one computer to another across a public access phone line. Now next is what? Digital to analog. So from digital to the phone line or to the wire, remember this. Now we have to see the bit rate. I have told you that there may be some examples for calculating the baud rate, bit rate. So this bit rate is the number of bits transmitted per second. It is usually greater than or equal to the baud rate. We have seen the baud rate. What is that? Baud rate is the number of signal units per second required to send those bits. Now, what is carrier signal? A high frequency signal that acts as a basis for the information signal by sender. Digital information is encoded by modulating the signal's amplitude, frequency, or phase. Bit rate equal to what? Baud rate into number of bits per signal element. Remember this equation for this digital to analog encoding. So in digital to analog encoding, what we have to do, we have to transfer the digital signal over from computers to over the telephone line. The computer generates the digital data, but the telephone system is analog. Okay, so that situation is here different. So what is the main factor in here is the transmission rate at which we have to transfer the bits. Okay, so for this there are the different methods. Okay, sorry. Next slide. First is what? Amplitude shift keying, ASK method. In this kind of encoding, this is abbreviated as what? ASK. What we are doing, we are transferring digital to analog modulation. Okay, the amplitude of the analog signal is changed to represent the bits. Okay, what we have done from analog to digital, we are what? Using pulses to determine the value. Now here we are using the, in ASK we are using the amplitude of the analog signal to represent the bits. The amplitude is varied from 1 or 0. There is only two value, 1 bit, okay, or 0, 1, 0, 1, 0. Keying means turning a transmitter on and off. Amplitude shift keying. On, there are only two states. 0 means what? Off, 1 means on. Highly susceptible to noise inferences. Noise is referred as random electrical signal that tend to generate errors in transmission introduced into a line by hit from circuit components or natural disturbance. So what happens in amplitude shift keying? High voltage is represented as 1, okay, and the low voltage is represented as 0. So in this form, the signal is what? Transmitted. So relationship between baud rate and bandwidth in ASK. So this is the amplitude, this is the frequency. So minimum bandwidth equal to n baud. This is the FC. Okay, it is what given by n baud by 2. And here it is what? FC plus n baud by 2. Frequency of the modulation, relationship between baud rate and bandwidth in the ASK. Next method is what? Frequency shift keying, FSK. Frequency is varied to represent binary 1 or 0. Just when a bit is encoded, the frequency changes and remains constant for a particular period. Bit rate 5, baud rate 5. So 1 baud, 1 baud, 1 bit 0, 1 bit. Okay. Frequency shift means when the frequency is changed, we are using that change for determining the value in terms of what? 0 or 1. So when it will be used? Frequency means what? Wait a minute. I will show you one more diagram if it is available in my PPT. FSK. Frequency shift Okay, the diagram is not present here. Just remember, next slide, no, it is not. So it is what digital modulation technique in which the frequency of the carrier signal varies according to the digital signal changes. FSK, frequency modulation, frequency shift keying. So this is the output wave with the help of what? Frequency shift keying. For a binary high input, wave is high in the frequency for a binary high input. Okay, so it is high means this is the low. Okay, and low in the frequency for a binary low input. The binary ones and zeros means the frequency is in between 1 and 0. We are, according to the frequency, we are what determining the signal. Means we are using the two oscillators for higher, one for the higher frequency and other for the lower frequency. Okay, so noise inference is not a problem because it's looking for a frequency change and doesn't care about voltage spike. So in this frequency shift keying, noise is not present. Next is the phase shift keying, PSK, phases. Okay. Phase is varied to everything we are using, frequency, pulse, phase, we are used to determine it to represent binary 1 or 0. Here what we are doing, the limited by the ability of the equipment to detect small differences in phases. This limits its potential bit rate, in which the sine and cosine inputs of a radio wave, sine and cosine inputs of a radio wave vary at a specific time, altering the phase of the carrying signal. Bit rate 5, baud rate 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 means this is one bit, all we are what transferring over this amplitude and time. Okay, so we will see it. When the phases are changing, that is the phase from this wave to this means the phase is changing. So we are determining the signal according to the phase change. That is called as what? Phase shift keying. Okay, everything we have to determine in the format of what? 1 and 0. Next is the quadrature amplitude modulation. See, quadrature stands for the 4. It is the hybrid. It is the combination of what? Amplitude and phase shift keying in such a way that we have maximum contrast between each bit, dibit 1 pair, quadrabit 2 pair, and so on. Theoretically, any measurable number of changes in amplitude can be combined with any measurable number of changes in phase. Uses more phases shift than amplitude shifts to reduce noise susceptibility. 4 QAM, 1 amplitude, 4 phases, 8 QM, 2 amplitudes, what? 4 phases. So these are the 4 phases here what? 1 2 0 1 0 0 0 1 0 0 0 1 1 0. So it is a hybrid quadrature amplitude modulation. You have to just draw the diagram. This is not so much important. The phase shift key amplitude, we have to remember the points with the help of the differences. Next is the analog to analog modulation, AM, FM, PM. Okay, so amplitude modulation, analog to analog. We have to what? Transfer the analog signal into the another analog signal without losing the data. The bandwidth of an AM signal is equal to twice the bandwidth of the modulating signal and covers a range centered around the carrier frequency. Carrier, this is the carrier frequency. AM radio stations need a minimum bandwidth of what? 10 kilohertz. Now amplitude modulation. We are using the radio station's amplitude. See the diagrams. It is mostly used for transmitting a radio wave. Okay, radio waves transformation. We are using this amplitude modulation, in which the wave signal what is transmitted by modulating the amplitude of the signal. It is often called AM and it is commonly used in transmitting a piece of information through a radio carrier wave. Amplitude modulation is mostly used in the form of what? Electronic communication. Okay, so see, this is the modulating baseband signal and we are what? This is the carrier signal. Okay, and this is the amplitude modulation, means the highest, we are not going by that rate, means highest signal, we are not increasing the frequency. So maximum amplitude remains the same as that of the carrier frequency. This is what your message signal. Next is the carrier wave, which is the high frequency signal and contains no information. And last is our resulting modulated, okay, wave, which is the message signal. This is our message signal and it contains the information. It is the carrier signal, which is the high frequency. Okay. So we have to draw, this is the our sender signal carrier and this is the AM signal. The bandwidth of the AM signal is equal to twice the bandwidth of the modulating signal and covers a range centered around the carrier frequency. Means the pattern may be like this, but this is not the information. The information is in this signal only. Okay, this is the amplitude modulation. Next is the frequency modulation. As there is what carrier signal here, the carrier frequency is there. The frequency of the carrier signal is modulated to follow the changing voltage level of the modulating signal. And the bandwidth of an FM signal is equal to 10 times the bandwidth of the modulating signal. An FM station needs a bandwidth of nearly 200 kilohertz. So we can see this is the modulating signal, this is the carrier frequency, okay, and this is the FM signal which we are modulating. Frequency modulation. We are setting our frequency in mobile also for the radio station. So that is the frequency modulation is the encoding of information in carrier wave by what? Differentiating frequency of the wave. This is our frequency modulation technique. Next is the phase. Phase means from 0 to 1. The phase it changes. So that is called as what? Phase modulation. This is the carrier. This is the modulating sine wave. And this is the phase modulated signal. See what we are. This is the highest, means there is no intermediate waves here. Here the intermediate waves are there, means what? We are encoding the signals. Okay, we are encoding the high voltage, low voltage according to the phases, amplitude of the modulating signal. This is our analog to analog transmission. So we have covered our third unit also. So this is somewhat actually higher or deep understanding, but just go on reading the books, you will remember the points easily. So thank you.